All right, let's get straight into it. We're going to tackle a key part of your AQA GCSE physics course, the required practical on thermal insulation. We'll cover everything you need to know, from the actual method and the analysis, right through to the kind of exam questions you're definitely going to face.
So here's how we're going to break it all down. First, we'll look at the key scientific ideas, the why behind it all. Then, we'll walk through the practical method itself. After that, we're going to dive into the results and how to graph them properly. Then comes the really important bit, errors and exam tips. And finally, we'll wrap up with a super quick summary of the key takeaways.
Right, let's get started. Before we even think about touching a beaker or a thermometer, we need to get our heads around the basic physics. Trust me, understanding this stuff is absolutely crucial for acing any exam questions on this topic. It all really boils down to a pretty simple question, doesn't it? You see, the universe loves balance. That means heat always flows from a hotter object, like your cup of tea, to the cooler surroundings. And this just keeps happening until everything's at the same temperature. So in this experiment, our entire goal is to find the very best way to slow that process right down.
So, one of the main ways heat makes a run for it is through conduction. I want you to picture the particles in the wall of a beaker, kind of like a row of dominoes. The hot water makes the particles on the inside vibrate like crazy. They then knock into their neighbors, which knock into their neighbors, passing that energy all the way along the chain until it reaches the outside. That's pretty much how heat travels through solids.
But heat also escapes through something called convection. Inside that hot water, the particles with the most energy actually move up to the surface. They cool down a bit, and then they sink again. This creates a kind of circulation, a current, that carries heat away. And that is why putting a lid on is so important in this practical. It literally stops that convection current and prevents a whole load of heat from escaping into the air.
And that brings us to the main event, insulation. Insulation is all about one thing, slowing down the transfer of heat. The best insulators are materials that are really bad at conducting heat. They have what we call a low thermal conductivity. A lot of the time, they work by trapping little pockets of air, because air is a terrible conductor. And in this practical, that's exactly what we're putting to the test.
Okay, theory sorted. Now, let's get our hands dirty, so to speak, with the practical method. Let's look at how we actually set up a fair test to figure out which material is the best insulator.
So, how do we actually do this? Well, first up, you wrap your beaker in whatever material you're testing. Next, you pour a specific amount of hot water in, and it is vital that you use the exact same amount every time. That's key for a fair test. You pop the lid on straight away to stop that convection we just talked about, and you stick a thermometer through the hole. You take a reading of the starting temperature, then boom, start your stopwatch. You'll then record the temperature at regular intervals, maybe every minute for about 10 or 15 minutes. Then you do the whole thing all over again with your other materials. Now this bit is so important for getting results you can actually trust. Your independent variable is the one thing you are deliberately changing, which in this case is the type of insulating material. Your dependent variable is what you're measuring to see the effect. That's the temperature of the water over time. Everything else, all those control variables you see listed, has to be kept exactly the same for every single test. We're talking the same volume of water, the same starting temperature, and making sure your insulation is the same thickness each time. If you mess those up, you won't know if it was the material making the difference or something else.
Right, so you've done the experiment, and now you've just got a page full of numbers. What on earth do you do with them? Well, this is the fun part, where we turn that raw data into something that actually tells us which insulator is the best.
Your results table should look a little something like this. You've got your time in one column, and then the temperature for each material next to it. Just by glancing at the numbers, you can already see a story forming, right? The temperature for material A is dropping way faster than for material B. That immediately suggests that material A is a pretty poor insulator, since it's letting heat escape so quickly.
But the best way to really see what's happening is to plot your data on a graph. You're going to put temperature on the y-axis, that's the vertical one, and time on the x-axis, the horizontal one. When you plot your points for each material and connect them, you'll get what's called a cooling curve. And this graph, it tells you everything you need to know. The key is the steepness of the line, what we call the gradient. A really steep curve means the temperature is dropping like a stone. That material is a poor insulator. But a flatter, gentler curve shows that the temperature is decreasing much more slowly, and that means you've found yourself a good insulator. So the single most important takeaway here is that you're not just looking for the material that ends up being the hottest at the end. You're looking for the one that has the slowest rate of cooling. That's the one with the shallowest, flattest line on your graph. It's the one with the lowest rate of energy transfer. Now, for the part that will really help you stand out in an exam.
Look, it's not enough to just know how to do the experiment. You've got to be able to evaluate it, to pick it apart and suggest improvements. This is where the top marks are hiding.
A classic exam question is to ask you to identify problems with the method and then say how you'd make it better. So let's put our critical thinking caps on for a second. Where could things have gone wrong, and how can we make our results more accurate and reliable?
Okay, here are some key points for you. First, using a digital thermometer is just better and gives a more precise reading, and you avoid parallax error. That's when you get a wrong reading because you're looking at the scale from an angle. Another thing, heat can and will escape through the lid and even the bottom of the beaker, so insulating those as well will give you a much more accurate result. It's also really important to start with the same temperature water each time, but that can be tricky to get perfect. And finally, the best way to improve pretty much any experiment is to repeat it and calculate a mean, or an average. This helps you spot any rogue results, we call them anomalous, that just don't fit the pattern.
Okay, we've covered a lot of ground there. Let's just wrap this all up with a quick-fire summary of the most important things you absolutely need to remember for your exam. Here it is, your final checklist. Remember, insulators work by slowing down the rate of heat transfer. To get valid results, you have to control your variables. Cooling curves are your best friend for analyzing the data, and the flattest line always wins. It's the best insulator. And please, don't forget, being able to evaluate the method is how you're going to get those top-tier marks.
And to finish off, here's a little something for you to think about. A vacuum flask is an incredible insulator. Its secret is a vacuum trapped between two silvered walls. So based on everything we've talked about with conduction and convection, can you explain why that design is so amazingly good at keeping your drinks hot? Thanks for tuning in, and I'll see you in the next one.